Hi everyone. Today we're going to be going over various geologic contacts and structures and what those all mean. Today we're going to look at different types of contacts as well as different types of structures that you may see, as well as orogenesis, how mountains are formed, why rocks undergo deformation and develop structures, what type of deformation causes which type of structures, as well as deformation in terms of plastic versus brittle. So a geologic contact is where two rock layers meet. So right where the two rock layers meet, we call that a contact. A conformal contact means that there's no loss of information or time between the two layers. So the second layer was deposited right on top of the first. Nothing happened in between the deposition that would have caused any loss of time or information in terms of there was no erosion of the first layer before the second was deposited. The second was deposited right away. We've captured this whole strata, the whole history of this location. An unconformity is where we have information missing. So something was removed before the new layer was deposited, and there are many types of this. Another type of contact is called an intrusive contact. So this is a contact of intrusive igneous rock. So this is where igneous rock has intruded into some other rock. And then we also have contacts caused by faulting. So this is where we have faults that cause new contacts that wouldn't have been there originally. So I'm going to go through each of these with examples and some really cool photos. So here we have unconformities where we have information is missing. Information meaning time, part of history is missing. Something was removed before the new layer was deposited. So you can see here, there's all these layers tilted, and then there's a new rock layer on top. So what happened here is all of these rock layers, they're sedimentary rock. They can't be, they were not deposited tilted. They must have been deposited flat. Everything was tilted and then eroded down, and then this layer was deposited. So there was a lot happening between when these layers were deposited and the top layer. So something similar here is these layers were folded, so there was some kind of compression squeezing these together, causing this folding before this layer was deposited. Something similar here. Again, we have these layers are a little bit folded, they're bent here. These layers are not, meaning that something caused this folding before we had the deposition of these top layers. So this is an unconformity where something is missing. Something in time, something in history, some information is missing because we can tell there's a gap in the strata, a gap in the story of these rocks. So an unconformity, there's a couple of different types. So a disconformity would be here. This is where we have information missing between parallel layers. So there's parallel layers, but we can tell that they weren't deposited right after each other because there must have been some erosion. So they're not perfectly flat contacts. They are eroded away contacts. So something must have happened between the deposition of this layer and the deposition of this layer. Angular unconformity means the old layers were tilted before the new layers were deposited. So these layers were all tilted before these layers were deposited. A nonconformity means new layers were deposited on top of eroded igneous or metamorphic rock. So somehow that igneous or metamorphic rock got to the surface, started being eroded, and then more sedimentary rock was deposited on top. So there's a couple different types of unconformities and ways that information can be lost. So here are some pictures in real life. Here is the angular unconformity. Here's the nonconformity. So they're relatively parallel to each other, but we can tell that something was missing. here is our disconformity. So here we have granite, which is an igneous rock, and then a conglomerate, which is a sedimentary rock on top. So it's a contact, but it's an unconformity. So there are also intrusive contacts. So intrusive contacts meaning where we have igneous rock intruding into pre-existing rock. So that creates, it's usually stripes of igneous rock. So here we have a strip of igneous rock. Here we have a bit of granite that intruded, it's quite large, into the rest of this limestone. And here across this mountain face we see there was an intrusion of igneous rock along this way. So this would have been a sill along at one point underground that has now been eroded to the surface. And we can also have faulting contacts. So contacts that are caused by faulting. So here we have a fault. Here's our fault line. So this would be a normal fault. So here we have our foot wall. So here it is shaped like a foot. Here are the toes, the heel, the ankle. Here's our hanging wall. And our hanging wall has slid down relative to our foot wall. You can see it must have slid down. So this is a normal dip-slip fault. But this layer, now in contact with this layer, normally wouldn't have happened other than being caused by this faulting. So faulting can also create contacts that are can be really, really, really cool to look at, for like these, for example. So we also, along with contacts, which are just layers between our different rock beds. Now, the contacts can tell us a lot of information, or they can tell us something's missing, which is not a lot of information. We also have geologic structures. So there's a lot of different structures that can be caused by types of deformation. So I'm going to go through examples of joints, faults, folds, and foliations. So these are all caused by some sort of deformation. So deformation, if a rock is deformed, that means it has undergone some type of deformation. Something has occurred to it since it was deposited. Undeformed rock means it has no geologic structures. It's in the same orientation, same spot as in when it was first deposited. Nothing has happened. Deformed means it's undergone some sort of change. Maybe it's been folded or tilted or metamorphized or cracked, so there's joints. This can be caused by orogenesis or mountain building. It can be caused by different types of stress. There can be displacement, rotation, strain, distortion, any type of deformation that changes the rock layer from where it was deposited. So here, deformation can be caused by displacement. So here we have a fault where we have a, let's see, so this would be, so this one is a little tricky because it's not as diagonal, but if we were to exaggerate, we would see the diagonal line looking something like this. We see the fault line between the green schist and the quartzite. So this would be a normal fault where we have the hanging wall sliding down. This is displacement, so displacing these rock layers. Rotation, where we have this, we know that this sedimentary strata would not have been deposited on a diagonal at any sort of angle. So sedimentary layers are always deposited completely flat along the surface of the earth. So this rock layer must have been rotated at some point. We can have distortion, where things are folded. They cause these really cool wiggly layers in our rocks. And then we can have different types of strain. So strain being change in shape. So there can be stretching, which elongates. There can be shortening, which contracts or squishes. Then there can be shear, which stretches out like a deck of cards. So different types of deformation depends on what type of material you are working with. So are we looking at brittle versus plastic are the two main ones. So when we're talking about a brittle material, This is where we generally see brittle material in shallow crust near the surface. And brittle material is going to break by fracturing, so by cracking, by breaking into smaller pieces, like dropping a plate on the ground is going to break. This is what we see at the surface. Our rock is always brittle at the surface. It is going to break into pieces. This is something common that you might see at the surface. At depth, however, the rock is under such high pressure and generally also higher temperature that the material moves like a plastic or a ductile. So it is going to move like a plastic. It is going to be deformed like a plastic. So this would be like if you had a ball of pizza dough and you dropped your geology book on top of it. The pizza dough is going to change shape. It's going to be deformed, but it's not cracking. It's not breaking into pieces. It's just stretching. It's elongating. So something like this here, where it looks like these rock layers were stretched, they were elongated, thinned out, that would be a plastic change, plastic deformation, where the material actually acts like a plastic or a plastic. So this will never be at the surface. You never find a ductile deformation at the surface. You will see this about 10 to 15 kilometers deep in the center of the Earth, towards the center of the Earth. So where we have that higher pressure and temperature, we're going to see our rock layers not necessarily cracking, but still deforming in a plastic way, not like the brittle layers at the surface. So with our brittle fracturing, the bonds within the minerals are actually breaking, so that's causing a permanent fracture, a crack in the rock. With plastic deformation, the bonds break, but they're quickly reformed into new bonds. So the atoms within the grains can actually rearrange, so it can change shape without any permanent cracks. So it's really just dependent on temperature and pressure if you're going to have brittle versus plastic. So the temperature causes the material to be softer because it's warm. The pressure prevents the rock from separating fragments. So the pressure keeps the rock together. So deformation rate. Brittle deformation happens very quickly. It's very sudden. The rock breaks. Plastic deformation happens very, very slowly over a long period of time. So slowly over many years, you're going to have that plastic deformation. So where would you expect to find earthquakes? Earthquakes are going to happen where we have brittle deformation, where we have cracking, where we have motion quickly. Not that very slow plastic motion, but the brittle cracking and fracturing. So this is going to be near the surface of the Earth. So it's generally going to be, earthquakes will always be 15 kilometers deep or above, because plastic deformation is going to happen below that, and we will not have earthquakes at that depth. So some different types of stress which can cause different structures on Earth would be compression. Compression is when an object is squeezed. So this can shorten in length but also thicken in height your material. So shortens in length but makes taller, so generally deeper and taller. We're going to have mountain ranges formed there. Tension is when you're pulling apart. So this is going to stretch in length and also thin in height. And then shear. So shear is where we have two surfaces sliding past each other. This isn't really going to change the thickness or the height of the crust, but it's just going to change the locations of things relative to each other. So orogenesis is what we call mountain building. Mountains, we call it orogenesis. Oro means mountain, genesis is formation. Mountains generally occur in really curved or very elongated curved belts. Origins are called mountain belts. So you'll notice that most of our mountains are in nice, long, curved mountain belts. So what kind of structures might we see on the surface of the Earth? So some structures, the first is called joints. So joints are where we see cracks in our rock. So we can very clearly see that this rock is very much cracked. This is not a solid piece of bedrock. There are many, many cracks, and they're quite parallel to each other, as well as here we see many joints in this rock face. So the rock is already cracked. So what can then happen is if those joints are able to fill up with another mineral, they are called veins. So we can often see strips of mineral within or strips of a different rock within the main rock. Those are called veins. So they're just joints that have been filled in with another mineral. So a mineral has filled in these pre-existing joints. So this vein is going to be a lot younger, a lot newer than the pre-existing rock, because the rock would have had to crack and then be filled in for that mineral to then solidify into this really cool looking vein structure. And it's not always this clustered. You can often see just one very large vein where there was one very large joint. It depends on the type of jointing that occurred in the rock beforehand. That's going to dictate what the veins look like. And then, of course, faults. So here we have a vertical motion. So you'll notice this is vertical motion, so it's going to be a dip-slip fault. So if we were to say, what fault is this? We would think, okay, where is the footwall? Where is the hanging wall? So here is our fault line. So this would be our footwall. So it's wider at the bottom than it is at the top, just like a foot with an ankle. And here's our toes. So our hanging wall is moving down relative to our footwall. This is a normal dip-slip fault. Another brittle structure, another fault line. So this one's a little bit harder to see actually, but this layer used to be parallel, or is the same layer as this. So our fault line is right along here. So this, where is our footwall? Where is our hanging wall? Here is our footwall. It's wider at the bottom than it is at the top, shaped like a foot. So this is going to be a reverse dip-slip fault because our hanging wall is moving up relative to our footwall. So when we look at our structures, some things that we generally will report on are the orientation of the structures. So we compare the structure to the horizontal, to vertical, and to north. So what is the angle to north? What is the vertical tilt? What has happened to this rock? Why is it no longer parallel to the surface of the Earth? So there's many different ways that this can be recorded and observed. So mostly when you're looking at some sort of structure, like this, for example, you want to make sure you are recording as much information as possible. So comparing the horizontal, the vertical, and also to north, trying to determine how this rock has moved in the past, how this rock has been moved in the past. So another type of brittle structure is folding. So layered rocks can be folded due to compression. So if we were to push on both sides here, push these rocks together, it would cause folding. They're going to scrunch up. Orogenesis, or mountain building, generally produces a huge volume of folded rock. So we can see quite a bit of deformation where there is orogenesis. We often see a lot of folded rock, and we can also see many different folding events. So over the course of orogenesis, there's going to be many different events of folding. So big mountain ranges can be a very good spot to see this incredible folding structure in the rock layers. Another type of fold is called an anticline. So where we see sort of the shape of an N, this fold, we call this an anticline. So here we can see that this fold has been folded into the shape of an N. So these layers were originally parallel to the surface. They are not anymore. The opposite is called a syncline. So it's like a U, or I think of it as the top of a Y. That's how I remember syncline. The one with the Y in it is shaped like a U. So here we see that U or Y shape here in this rock layer. So this again was caused by folding. This is called a syncline. So you can see syncline and anticlines right next to each other. For example, anticline, syncline, anticline, syncline, anticline there. So they're often near each other. So another type of fold is called a monocline. So this is where it looks more like a step. So that first layer is kind of folded and collapsed over, but it's not a perfect curve. It looks more like a step. That would be called a monocline. So folds are really interesting. They're absolutely amazing to see in person. The fold, we generally will report on the severity of the angle. So like how folded is the fold? Is it a really, really broad sloping fold, or is it totally folded and squished together? We can also determine, is it a plunging fold? So is the hinge of the fold plunging, or is the hinge still parallel to the surface of the earth? So folds are some of my favorite things to see as you're driving around, especially in Southern California. If you go inland a bit, you can see quite a few of them, and generally those will be caused by compression. So folding is caused by compression. We can see quite a few down by the San Andreas Fault if you've ever been over there. I highly suggest going.